Hi guys, thank you for joining me today. Um, I will do module number 3, average, normal, and shear stresses. Previously, in this course, we covered that we have two major types of stresses. The first one is called normal stress. In this case, the intensity of the applied force is perpendicular to the cross-section. Perpendicular to the cross-section. The second type is called shear stress. In this case, the applied force will cause intensity parallel to the cross-section. Parallel to the cross-section. So just a reminder, for the cross-section under tension, the stress distribution can be something like this. So the stress direction is perpendicular and causing pulling to the cross-section. If the cross-section under compression, in the case of normal stress, so the stress will be looks like this, pushing the cross-section. For the shear stress, I don't care about the direction, but the direction will follow the applied force, but the stress is parallel to the cross-section. The units for this stress is represented by force per unit area. We have two systems, SI system. So the force in Newton, the cross section in in meter square. So it will be Newton per meter square, which can be called Pascal. Or the force in Newton and the cross section area in millimeter square. So it will be Newton per millimeter square, which is called megapascal. If we are using the system of units, the force in pounds, the area in inches square, so it will be PSI, or kb per inch square, which is called KSI. So the stress is a value measured in units, force per area. This is the unit of the stress. One of the types of normal stress can be classified into axial stress and bending stress. We discussed this in the previous video. We have axial stress and we have bending stress. We will focus in this video, in this module, on the axial stress. Actually, the average normal stress caused by axially loaded bar, caused in an axially loaded bar. Just a reminder, the applied force P on any member can be tension, like this one, or can be compression, like this one. So if the force is pulling the member, it will be tension. In this case, the stress caused by this tension force is called tensile stress. The force which is pushing the member will cause compression. In this case, the stress will be called compressive stress. If you would like to figure out the value of the axial stress or the normal stress, you have to divide the applied force by the area of the cross section. Keep in your mind, this force is applied to this cross section. So if you are able to figure out what is the area of this cross section, then divide the applied force by this area, you can get the average axial stress or the average normal stress, both of them the same meaning. So sigma is the normal stress value, the average normal stress value. P is the applied force, and this force can be tension, can be compression. Area is the cross-section area of the member, this cross-section area. Does that make sense? So just a reminder, the applied force can cause tensile stress if the applied force is a tension force. The applied force can cause compressive stress if the applied force is compression force. Just a reminder, this stress value equal the applied force divided by the cross-section area. Also, if the stress is tensile stress, it will be positive. If the stress is compressive stress, it will be negative value. This one is positive, and this one will be negative value. That makes sense? We have a few examples. The first example, we have a bar with constant cross-section. The width is 35 millimeter. This width, 35 millimeter. And the thickness of this bar is 10 millimeter. And this cross-section is constant throughout the bar. We need to figure out what is the maximum average normal stress in this bar. That makes sense? Looks like this bar is consisting of three parts, part AB, part BC, part CD. So I have to consider each part to figure out the average axial stress in each, and then I can tell you which part will have the maximum normal stress. So let's start with part AB. I would like to figure out what is the axial force in this part. So I will go back to engineering mechanics, how to figure out the axial force in a part of a member. So I will do cut, and I will decide to use the left part, or I can use the right part after I did cut in part AB. So to make it more easy, more simple, I'm gonna use the left part. So here is the left part. I did cut here, and I have at A, I have a force equal 12 kilonewton. So from engineering mechanics, if you apply summation f of x equals 0, we must have a force here in opposite direction to 12 kilonewton equal also 12 kilonewton to make sure summation f of x equals 0. This force is pulling the member AB, or pulling the section in member AB. That means this force will be tension force. So the value of the stress in part AB will be positive 12 kilonewton divided by the area of the cross section. The area of the cross section is 35 millimeter by 10 millimeter. Keep in your mind, this bar looks like this in the real, in 3D, looks like this. This width equal 35 millimeter. The thickness equal 10 millimeter. So this cross section, which is under the force 12 kilonewton, will have an area equal 10 by 35. So this one in kilonewton, and this one in millimeter square. So I do recommend to make your units one of these. So I will use Newton per millimeter square, which is megapascal. That means I do recommend to multiply this force by 1000. So the numerator will be in Newton, the denominator in millimeter square. So the stress will be positive. Positive, why? Because it's a tensile stress. Tensile stress, why? Because the applied force is tension force. That makes sense? So 12,000 divided by 35 times 10. So the value equal 34.3 Newton per millimeter square or mega Pascal. This is for part AB. Let's do part BC. For part BC, I will do the engineering mechanics part. So I will do cut in part BC. After I did the cut, I have two options to use the right part or to use the left part. It's up to you. Both of them will give you the same answer. It's up to you. So I'm gonna use the right part. So here is my cut. Here is the right part. Here is point C. Here is point D. I have a force here, 22 kilonewton. I have two forces here, each 4 kilonewton and 4 kilonewton. That makes sense? Don't forget any from the right part. If you apply summation f of x equals 0, we should have, not should, we must have a balance. That means I have to get another force here in this direction. This force will equal, I think, 30 kilonewton. To make sure, this 22 plus this force, 4 plus this 4 will equal 30. That means we must have another 30 on the opposite direction to make sure summation f of x equals 0. That makes sense? I think this force in this position related to this cross-section is pulling, not pushing. It's pulling. That means it will be tension. So, the stress in part BC will equal the applied force on this cross-section, 30 kilonewton. So I will multiply it by 1,000 to be in Newton, divided by the cross-section area, which is the same, 35 by 10 millimeter square. So the final value will be positive because it's a tensile stress. How much? 30,000 divided by 35 times 10. So the value will be 85.7 megapascal. Megapascal means Newton per millimeter square. The last part that I have to consider is part CD. So I will do the engineering mechanics part first. I will do cut in part CD. I have two options, both of them correct. I can use the right part, which is the little one, or I can use the left part, which is very big. Both of them will give you the same answer, the same answer. So I'm gonna use the right part. Here is the right part. Here is your cut. And here is point D. And I have a force here, 22 kilonewton. So to apply summation f of x equals 0 and make sure we have balance, we must have another force at this cut in this direction to make balance equal 22 kilonewton. This force in this position and this direction related to this cut or related to this cross section is pulling the cross section or pulling the member. If it's pulling, it will be tension. So it will be tension force. So the stress in part CD will equal the applied force 22 kilonewton. I will convert it to Newton by multiplying by 1,000 divided by the area of the cross section, which is 35 millimeter by 10 millimeter. So the value of the stress will be positive because it's a tension. That means we will have tensile stress. How much? 22,000 divided by 35 times 10. I got 62.85 megapascal. So the highest value of stress, which is the maximum stress, will be 85.7. So the maximum stress will be 85.7 megapascal. Positive means tensile stress. That makes sense? This is how to solve this kind of problem. We have to combine the engineering mechanics to figure out the applied force, and then we have to apply the mechanics of material to get the average normal stress. We have another example here in example 2. We have a light lamp is supported by two cables, BA and BC, in this position. The diameter of member AB is 10 millimeter, and the diameter of member BC is 8 millimeter. We need to figure out the average normal stress in each rod or in each member, BA and BC. First of all, I have to start with the engineering mechanics part. So, from engineering mechanics and from equilibrium, this weight, which is 80 Newton, is hanging. 80 Newton is hanging by this cable with a force F BC, and this cable with a force F BA. That makes sense? So the first step, we need to figure out what are the forces in this member and the force in this member, BA and BC. So this weight, which is 80 Newton, is hanging by these two cables. So these two cables will have a force, will have forces FBA and FBC. This angle is given 60 degree. So I can break this force to two components. FBA can be broken to two components. One horizontal, FBA cosine 60, and FBA, I'm sorry, PA sine 60. Also, the force FBC, it's not given with the angle, but we have right angle triangle. That makes sense? So if we assume this angle is theta, so I will have horizontal component FBC cosine theta and FBC sine theta. Keep in your mind, this angle theta will equal to this angle theta. This one theta will equal to this angle theta inside the right angle triangle. So this right angle triangle, which is 3, 4, 5, this is your angle theta. So I can say sine theta equal 3/5, cosine theta equal 4/5. So I can remove this cosine and put 4/5. I can remove this sine and put 3/5. Then I will apply the two equilibrium equation. Summation f of x equals 0. In x direction, we have positive 4/5 FBC. We have negative FBA cosine 60 equals 0. I cannot do anything because we have two unknowns, FBC and FBA. I will apply summation f of y equals 0. In y direction, I have positive FBA sine 60. I have positive 3/5 FBC, and I have negative 80 equals 0. I cannot do anything also for this equation because I have two unknowns, FBA and FBC. Then I can solve this equation and so this equation together to figure out the unknowns. Let me simplify this one. So we have positive 0.8 FBC, negative cosine 60 is 0.5. FBA equal 0. I can simplify this one. So I will have sine 60, or I can switch. I will have positive 0.6 FBC, positive sine 60. I have 0.86 or 0.87 FBA equal 80. Solving the two equations will give you the value of FBC and the value of FBA. How to solve the two equations together? It's very simple. I can say from equation number 1, FBC will equal 0.5 divided by 0.8 FBA. I just moved this term to the other side. It will be positive 0.5 FBA and then divide it by 0.8. So this is the first one. In the second one, I will remove FBC and put this value. So I have 0.6 time. In this equation, we have FBC. So I will remove FBC and put this term. 0.5 divided by 0.8 FBA plus 0.87 FBA equal how much? 80. From this equation, I think I have only one unknown, which is FBA. I can figure it out. So 0.6 times 0.5 divided by 0.8 plus 0.87 divide 80 inverse. I think this value will be 64.25 Newton. Let me check it one more time. 0.6 times 0.5 divided by 0.8 plus 0.87. Yes. If you come back here and put FBA 64.25 times 0.5 divided by 0.8, I got the value of FBC will equal 40.16 Newton. So FBA 64.25 Newton. FBC equal 40.16 Newton. Now I can figure out the axial stress. Keep in your mind the stress sigma equal the force divided by the area. I already find the force for each member. So if you would like to figure out the stress in member BA, I have to put the force FBA divided by the area of member BA. The force in member BA equals 64.25 Newton. Member BA for AB has a diameter 10 millimeter. So pi divide 4 times diameter square. This is the area of a circle with a diameter 10 millimeter. So I can figure out the stress, which will be Newton per millimeter square, which is megapascal. So 64.25 divided by pi divide 4. So the stress will be positive 0.818 megapascal. I forget to highlight that these forces are tension forces for one reason. The value is positive. That means I assumed the correct direction. I assumed the correct direction for FBC and FBA, which is tension. So these forces will be in tension. That means the stresses will be tensile stress. If you would like to figure out the stress in member BC, I have to divide the force in member BC by the area of member BC. The force in member BC equal 40.16 Newton. And the diameter of member BC has a diameter 8 millimeters. So by divide 4 times 8 square, this one in millimeter square. So the stress will be 40.16 divided by divide 4 times 8 square. So the stress will be 0.798 megapascal, which is positive, means tensile stress. So I calculated the average normal stress in each rod AB and BC by applying first the engineering mechanics part to figure out the forces in these rods, and then apply the mechanics of material part to figure out the average normal stress, sigma equal force divided by area. So the force in each member is known and the area of each member is known, so I can figure out the axial normal stress. We have one more example. For the shown rod, we need to figure out the average normal stress developed at point A, B, and C for this rod. The diameter for each part is given 0.5 inch in this part, 1 inch for this part, and 0.5 inch for this part. Since we have 3 points or 3 parts, so I'm gonna divide my solution to 3 parts. The first one, to figure out the stress in point A. So at point A, I'm gonna do cut. Once you did this cut, I have two options. I can use the left part after the cut, or I can use the right part after the cut. It's up to you. I do recommend it to use the smallest part, which will be more easier. So I'm gonna use the left part. Here is the force applied, 3 kb. And I did cut here. From engineering mechanics, and to apply summation f of x equals 0 to make sure we have equilibrium, we must have another force in this direction equal 3 kb to make equilibrium, to make summation f of x equals 0. This force in this direction related to the member under consideration, this force is pulling. So this force is tension. That means the applied stress sigma at point A equal the applied force 3 kb. I'm gonna multiply it by 1000 to be in pound. Or you can keep it in kb. That's fine. It's up to you. It's up to you. If you keep it in kb, it will be KSI. If you convert it to pound, it will be PSI. It's up to you. And the cross-section area for this part at point A is a circle with a diameter 0.5. So I have by divide 4 times this diameter 0.5 square. So I will keep it in kb. I will not convert it. So the number will be logic a little bit. Kb. And this one will be an inch square. So the stress will be 15.3 positive kb per inch square or KSI. KSI. And this stress is tensile stress. For part or for the second point, which is point B. I will do cut at point B. So please forget the first cut. We have right now a new cut at point B. This cut will divide your member to two parts, one on the right and another one on the left. It's up to you to select whatever you want. So I'm gonna select the right one. So I have here the right one. Looks like this, and make it bigger. And here is your cut at point B. Keep in your mind, we have a force here to keep, and I have another force here. How much? 8 kip. To make sure the summation f of x equals 0, to make sure we have equilibrium, this 2 and this 8, that means I must have another 6 kip in this direction. So this 2 and this 6, both of them to the right will be 8, and this 8 to left, so we have equilibrium. This force 6 kilonewton, I'm sorry, 6 kip related to this part or related to this cross section or related to this cut, it's pushing. Pushing. Pushing means we have compression. The force is pushing the cross section. The force is pushing the part you are working on. So we have compression. So the stress at point B will equal negative. This force is 6 kip divided by the area of the cross section at point B. At point B, the diameter of the member is 1 inch. So I have pi divide 4 times 1 inch square. This is 1 inch square. So the stress will be negative. Negative means compressive stress. The applied force is pushing, not pulling. So 6 divided by pi divided 4 times diameter square. So the value will be negative 7.6 KSI, which is kip per inch square. The last part or the last point, which is point C. Point C. So I will do cut at point C. So please forget these cuts. I will do new cut at C. So I have two options, this little part on the right or this big part on the left. For me, both of them will give you the same answer. I'm gonna use the right part. So I did cut here. I have a force here to kip. For equilibrium summation f of x equals 0 from engineering mechanics, we have to have a force here in this direction to make equilibrium equal to kip. This force in this direction related to this part of the member is pulling. So we will have tension force. That means the stress at point C equal the applied force, which is 2 kip, divided by the area of the part of the member at point C with the diameter 0.5. So pi divide 4 times 0.5 square. This stress will be tension, which is tensile stress. Positive, how much? So it will be 10.2 KSI. tensile stress. So I can figure out the average axial stress or average normal stress. First step, we have to use engineering mechanics to figure out the force in the member, and then we can apply your stress equal force divided. That's it. We have another example. This one is very easy. We are given a cross section, looks like I section, and we have applied force 15 kb, and we need to figure out the average normal stress. It's very simple. The average normal stress equal the applied force divided by the area of the cross section. So we need to figure out the area of this cross section. What is the area of this cross section? So the area equal, we have 1 inch times 4 times 2. This rectangle has an area equal 1 times 4. And this rectangle is repeated one more time on the other side. This is the reason I multiplied it by 2. Plus this web is a rectangle with an area equal 1 times 4 also. So we have 12 inches square. This is the area of the cross section. So the applied force is 15 kb. The area of the cross section is 12 inches square. So the value will be negative. Why negative? Because this force is pushing the cross section, pushing down, pushing the cross section. So we have compression. 15 divided by 12, it will be negative 1.25 kb per inch square or KSI. So we have compressive stress. We have compressive stress, and this is the reason why I put negative value. This is for average axial stress. In the next video, I'm gonna do the average shear stress.